Okay, so let's start the second segment of our discussion, the second part to be precise, and we will continue our discussion from where we left off in the last video. Um, in the last video, we discussed about the point of rotation of the best fit line, or the point about which the best fit line rotates, the x bar and y bar, x bar, y bar. And in this video, we'll be dissecting the OLS formula in depth. Um, for me, which is the juice of the discussion, as I'm saying it again and again. Let's make some screen real estate first. Let's have some blank space to start with. And the first thing that I will do is write the formula, of course. Okay. So the formula, let me commemorate this before I start the discussion. Okay, so the literary formula for OLS is covariance between the variable x and y divided by variance of x, right? Now, if you have, as I've previously said, that you need some prerequisite knowledge of these topics before starting on this video. Even though I am discussing everything, but it'll be good for you to have the prerequisite knowledge of everything that we are discussing in this video. At least not the things that I have said, not the things that I am discussing, but the usual and the traditional stuff that is being taught. So here, for example, you should know that the variance, that the root over variance is standard deviation. Root over variance is known as kind of standard deviation, and standard deviation is the average distance of a point from the mean in the data set. Yeah, in the independent data set or the dependent data set. And when I've written variance of x, then what I mean, it's just a representation of average distance of a point in the data set, in the independent data set, in your independent variable. Okay, so standard deviation. Now let me expand this formula into its mathematical form, and then we'll start to analyze it. So first, let me kind of break this formula down into its mathematical form, and then we'll start to analyze. Then we'll start an analysis. Okay, so summation x minus x bar, y minus y bar divided by n minus 1 whole divided by summation x minus x bar squared n minus 1. The n minus 1 factor gets cancelled out, and you're left with summation x minus x bar y minus y bar, and here we have summation x minus x bar squared. Okay, so this is one of the forms that you might be familiar with, that you might have seen in your textbooks. There's one more form in which you can write this equation by performing some elementary manipulations, some basic elementary mathematical manipulations. Let me write that down as well. So if you break this formula down from inside the summation marks, then what you'll get is xy plus x bar y bar plus minus x y bar minus y x bar. If I have not, yeah, I think it's right. And here, so here it's actually xi yi, but I think I'm not ready to like write each and everything, because we're not obviously discussing about the formula itself, right? So that's why I'm kind of writing it in such a way that as you can see, because this is not a discussion, right? We're not discussing about the formula. We are just very interested in its analysis, kind of. So x squared minus x bar, I'm sorry, plus x bar squared minus 2 x bar x. Now summation can be broken down onto these plus and minus symbols. This is the property of summation actually. Now it'll become summation xy plus summation n times summation. So it will be summation x bar y bar and x bar y bar both are constants. So it'll be n times x bar y bar minus y bar summation x minus x bar summation y. Okay, make some space again. It'll be summation x squared summation x squared plus this n times some x bar squared. Again, x bar is a constant, so it'll come out with a summation mark. N times x bar squared minus 2 times x bar summation x. Yeah. Now I hope again you are aware about the formula for average, even though there's some bit of discussion that I have to do before about averages before we start on the discussion. But I hope you're familiar that x bar is equals to 1 upon n summation x, right? Xi, whatever it is. So n x bar is equals to summation x, right? So for summation x, we can replace summation x with n x bar over here, and we can replace summation y with n y bar over here, over in this case, and in this case we'll replace it here as well. So summation xy plus n x bar y bar minus if we replace n x bar over here, then what we'll get, we will be getting n x bar y bar, because if you substitute n x bar over here, then you will have n x bar y bar, and then again you'll be having if you replace summation y will be substituted by n y bar is equals to summation y, so it will become again n x bar y bar. These two terms will be cancelled out. Make some space. Summation x squared plus n x squared minus 2 times x bar n x bar squared 2 times x bar times n x bar, right? It will become summation and it will actually eventually become 2 minus 2 times minus 2n times x bar squared minus 2n x bar squared, right? And minus 2n x bar squared plus minus 2n x bar squared plus n x bar squared will be minus n x bar squared, right? If you do the subtraction over here, then it will become like this, minus n x bar y bar whole divided by n summation x squared minus x, I'm sorry, n x bar squared. Oh, I think I have wasted, I should not say wasted, but I have actually spent 10 odd minutes of my video on something which is actually not related to my work, actually not related to the main essence of the video for which I'm making the discussion. But what I'll do during the editing part is I'll just speed up this portion so that you don't have to go through all this, because 10 odd minutes it's a very long time on something which is not related. Nonetheless, this is same, I'm sorry, so this is same as this one, okay? Even though this is what we will focus on, this is the form that we are actually interested in. Okay, let's start formally the discussion. Okay, let me choose another color. Now what I want to ask you is, the first thing that I want you to observe is that let me write this formula in a bit different way, which will be convenient for our analysis, because the kind of route that will be taken to analyze this formula, actually it will be very helpful for us to do that. As you can see over here, we are dividing it by variance, right? As I have said, that variance is actually standard deviation squared, right? Or root over variance is standard deviation, whatever it is. Therefore, what we'll do is we'll actually write the denominator part of this equation as standard deviation of x times standard deviation of x. This is a form that will help us better analyze what's going on, according to at least my analysis. This is the form that I'm most comfortable with. Okay, now let me ask you a question before, as we are starting our discussion, that what happens when you multiply two values? The values are measured on axes which are perpendicular to each other. And by that I mean, you know that this is some value on the x-axis and this is some value on the y-axis, right? Now what happens when you multiply two such values which are measured on the axes which are perpendicular to each other. Let's say I pick some random point x naught and some random point y naught. Then what does x naught y naught represent? Most of you would have given the right answer. It's this area. It's a rectangular area enclosed by this particular figure. It's this particular shape, right? This particular rectangle. So here, so first what we are doing is we are breaking down this formula into its literal form. I mean, what in essence we are actually doing. This is what we're trying to find out. Um, so it's nothing but some rectangular area. This is what I want you to take notice of, um, first of all, right? Okay, so this here is some rectangular area. Rectangular area. Okay, now what is the significance of the summation mark? Now it is asking us to sum up all the rectangular area corresponding to every point in our data set, in our data plane, to be very precise to you. Let me make the data plane first, then we'll come back to it again. Let's say this. Okay, don't do that. I think that'll do the work. Yeah, I mean, who cares about the pair of axes, right? We are more interested in the data itself. So yeah, let me make some data points for us to analyze a proxy or a dummy data point, a dummy set of data points on our pair of axes on our plane. Okay. Here we go. So what is asking us to do is, for each of the x and y's that we have, for example, this is some x1 y1, this is some x2 y2, okay, x2 y2, and so on and so forth. For each of these points, we have to calculate the rectangular areas. We have to calculate the rectangular areas, and we have to sum those areas up. Okay, before moving on, there are the prerequisites. I know that I'm instead of starting on with the main discussion, I'm just brushing on the prerequisites only, but there are some things that I need you to focus on, so that you can kind of take the taste of this particular discussion to the maximum extent that is possible, kind of. So for that, you need to take care of some mathematical nuances that I am discussing. The first thing is, here some transformation is being performed. If you have studied transformation of axes, shifting of origin in your high school mathematics, or wherever if you have studied transformation of axes, then you must be knowing that in these two formulae, in the expression above, or you can say in the numerator part of our expression, the numerator is performing some transformation on the axes. Now, what kind of transformation is it performing? Well, first of all, you have to know what transformation is. So when I say transformation of axes, then what I mean is you are shifting your origin, or either you're shifting your origin or you're kind of rotating your origin about its point. Okay. So here we are not actually rotating the not the origin, I'm sorry. So transformation means either you're shifting the position of the origin, or you're rotating the axes about the origin. Yeah, I think that is a better way to say it. So we are not actually rotating the axes in this case, but here we're actually shifting the position of the origin from its usual place where you see it to some other place. Now for that, you first need to understand what an origin does and what is an origin in a coordinate system. So in a coordinate system, an origin, an origin or a zero, it separates the positive and the negative side of the axis, right? So on the x-axis, the zero separates the positive and the negative side. On the y-axis, the zero separates the positive and the negative side. So this is the property of an origin. Now, any point having this property is origin. Okay. So what is happening in this case? X minus x bar, what I am claiming is x minus x bar shifts the origin of the coordinate system to x bar. Why am I saying that? Because now if you see, any point taken to the right of x bar will have a positive value, right? Because if you take any point which is to the right of x bar, then x minus x bar will always be positive. And if you take any point to the left of x bar, then x minus x bar will always be negative, right? So what happened in this case is we have actually performed the transformation of axes and shifted the origin to x bar. And here we have shifted the origin to y bar. Now, if you, in this particular case, in the second case, let me show you. In the second part of the expression, in the first part we have shifted the origin to x bar. In the second part we have shifted the origin to y bar. If you apply these two transformations simultaneously, then the origin gets shifted to yes, you guessed it right, it's x bar y bar. So the origin gets shifted to x bar y bar once you apply the transformation, once you apply such transformation on your expression. So for your expression, for your expression, the origin is shifted to x bar and y bar. So this is something that I want you to take note of. So the shifting of origin part. Okay, so now we have a new origin for our expression, right? Now we have a new origin for our OLS, and if it is having such new origin, then we should highlight it as well, right? So let me choose purple. Yeah. So this is the, let's say this is x bar and this is y bar. Here is that special point. This point is very special, as I've already told you in the previous part of the discussion as well, that this point x bar y bar, absolutely amazing. Yeah. Now, okay, so and the second thing that I wanted to discuss is, okay, let's first let's again come back to the formula itself. Here we are finding the areas for all of our points. Now our origin has been shifted to this point, so this is the rectangular area that we care about. This is the rectangular area that we care about. This is the rectangular area that we actually care about. So we have to find the areas for all of the rectangles because this is what the formula is asking us to do, right? It is asking us to calculate the areas for all of those rectangles. For each and every point, we have to calculate the areas of the rectangle, corresponding areas, and we have to sum them all up. We have to sum them all up and divide it by this n minus 1 factor. So what we're actually doing cumulatively is we are finding the average area of the rectangle, of a point rectangle. Let me call it a point rectangle. That would be better. So we are actually finding the average areas for all of the point rectangles that we have. Okay, now comes the second prerequisite for to actually dive deeper into the discussion of this formula, and that thing is um, the discussion about averages. So it's not that I am feeling that you guys, the ones who are watching this video, are incompetent and they don't know what averages are, but for us to be on the same page, I'm just kind of discussing in brief of what I think averages are and what I think averages represent. Now, when I say averages, then there are actually two assumptions that I'm making. Uh, Actually, those assumptions can be distilled down to one, but let's just go with two so that we are clear or we are concrete on our statements. Now, if we don't have so tell me if you agree to my statement or not. If our data doesn't have any outliers or it is not skewed, okay, so no outliers and no skewness, or maybe close to negligible skewed. If even if it is skewed, then it is negligible, and you don't have any major outliers in your data set as well. Okay, so negligible skewness and no outliers. So if your data set has no outliers and negligible skewness or no skewness, it is not skewed, then average represents the majority proposition of the data set, right? For example, if we say the average, for example, if we in our everyday lives, when we use the word average, we more often than not mean the average view. When we say we more often than not mean the majority view of whatever thing that we are discussing the average about. So if I say average view in the market, then what I'm actually implying is that the majority of the view in market is in that direction, let's say. So if I say that the average view in the market is heading in some direction X, then what am I actually implying? I'm saying that the majority of the views in the market are heading in that direction, right? So again, if you're thinking that the discussion is focusing on spoon feeding too much, then this is not the case. It's just that I want us to be on the same page. Okay, so let's assume some data points, and okay, so here I have made some hypothetical data points, and if I ask you, where should the average of the data point lie? I mean, if I ask you to find an average point, a representation of this data set, what point will you find, and where will that point be? What will be the position of that point? So if you ask me, it will obviously lie in the high density region of this data set, right? Most probably it will be lying in, most probably, I mean, it will be lying in the high density region of the data set. Again, I have stated the assumptions that I'm making: no outliers, negligible skewness. So if you don't have any outliers, then majority average is a very good way to get to the majority proposition, the majority view of what is happening in the sample. Is so it's a very good way to get, it's a very good way to understand the majority view of what's happening in the sample, right? So so an average point is kind of represents so when you take out an average point, it kind of represents the uh, mm, so it represents the majority it represents the majority, right? So an average point represents kind of the majority view of the data set, and it lies in the high density zone, obviously, because the more points so if an area contains more points, then obviously the average of the data set will be lying, the probability that the average of the data set will be lying in that region will be high, right? The region having high density of points. Enough, I guess. So it's the representation of a majority proposition, averages. So when we average this point, when we are finding out the average, what we're actually doing, is we are finding an average of our we are finding an average of all the points that we have in our data set. Obviously it will be lying somewhere over here, maybe, because I think even if it is not, then let me make it high density zone. Maybe I'll make some more points over here. So most probably it will be lying the average point will be lying somewhere over here, maybe, right? But not so fast. Once you'll perform the calculations in the numerator data set, once you'll perform the calculations in the numerator part of this equation, what you'll actually get is a value. Let's say that value comes out to be A average. Now if I ask you, the average area of the rectangle comes out to be A average, okay? Maybe I'll write it as AV. Now if I ask you to draw the rectangle with an area of A average, then there are actually infinite pairs of lengths and breadths that you can come up with to draw the rectangle. And by that I mean, if let's say the A average comes out to be 12, right? Obviously when you do the calculation, you won't get length and breadth separately, right? You won't get the lengths and breadths separately from the numerator. So you'll get a value, and the area itself is not enough to draw the rectangle. You need lengths and breadth separately, because if the area comes out to be 12, let's say, then one of you might draw a rectangle with length 4 and breadth 3, such that the area comes out to be 12. Some of you might take length as 6 and breadth as 2. Still the area comes out to be 12. So both of you are right, but kind of you can see, so here you can see the problem, right? There are actually infinite pairs which can be made such that the product comes out to be 12, and this is what happens in this case as well. There are infinite pairs that are possible. So to make our analysis easier, what we'll do is we'll take the help of the denominator. In the denominator, we have imagine it to be a square, kind of a square with the sides as standard deviation of x. we'll take the help of, when I say we'll take the help of denominator, then what I'm kind of that one then what I'm trying to do is, um, um, we are kind of I'm kind of standardizing, I'm kind of no m- so to make our analysis easier, we are standardizing, or we are making the numerator and the denominator um, such that our analysis becomes easier. So that's why I'm taking help of, because if you have the liberty to choose any value as length, why not to choose the most easiest value? I mean, if you get the area and you can choose any value as length, and corresponding you'll get the breadth, right? So if I choose the length to be, let's say, length AV, then the breadth AV will be equal to AAV upon LAV, right? This is what it is. So whatever length you can choose any length, and the breadth will come correspondingly. So this is the liberty that you have. So I need to take the advantage of this liberty and choose some standard values. And what's more standard than the standard deviation itself? So that's why. Because see, numerator can also be interpreted. Numerator can also be interpreted as some area, right? Because here also we are doing x minus x bar squared. So I am assuming it to be a rectangular area. I'm sorry, I'm assuming it to be I'm assuming to be the area of a square, right? Square having the sides standard deviation of x and standard deviation of y. And that's why I've said that this is a more convenient form for me to move along this discussion. So standard deviation of x times standard deviation of x, this is what you will get, right? So what I will do is I will assume the length of this area to be standard deviation of x, and the breadth will be AAV upon standard deviation of x. I don't care about the breadth. What I have done is I have made both of the lengths same. Both of the what I have done is I have made the lengths of both of these shapes the same, the square as well as of the rectangle. Let me draw the square first, because square is easier to draw. We're just kind of multiplying the standard deviation values. We're just multiplying the standard deviation values here, right? So let's assume the standard deviation length first. So if this let's say this is standard deviation of x. Maybe it'll be a bit longer, but we'll take that. And this is the standard deviation of x as well. So we are talking about this square. Assume it to be a square, even if you don't think it is. This is a square, and this is also a square. Now the advantage of our analysis comes out here in this manner. The advantage of our assumption, actually. So not quite correct. Yeah, let's say this is that the point is at a good position, actually, even if I've drawn it randomly. So this is the average point. Let me choose another color to highlight it. This is the average point. If you're finding it difficult to see that point, let me choose purple. It's not a good color. Maybe blue was better. Yeah, so this is that average point, or this represents the average point of our data set, right? This particular point. and this is the standard deviation of x comma standard deviation of x, and this is our average point. Okay, now what we have done by performing these kind of manipulations is that, okay, so let me divide the discussion into two parts from here onwards. So the first, so there actually, now we have got to the main part of our video. So the first perspective to analyze this, the formula of OLS, is to is what I call the intuitive perspective, and by that I mean that imagine this point to be the point where your model currently is, this point. Okay, and this point is where your model needs to be. So first, before that, let's see what we have done in our formula first. So we have in the numerator we'll have standard deviation of x times this b divided by standard deviation of x times standard deviation of x, right? The standard deviation of x part will cancel out and you will be left with b standard deviation of x. So it's the ratio of the heights. First of all, it's the ratio of the heights between, this is the b, this is b, and this is standard deviation of x. So b upon standard deviation of x is actually giving you the slope, right? This is the slope estimation formula for in OLS. In OLS, this is the slope estimation formula. So what is it actually doing? Now, if you see closely, this is just the ratio of the heights of these two rectangles or these two figures. Now, this expression is actually telling you how much scaling do you need to perform on standard deviation of x to get to point B. Okay, so it is to say as if this is where we are. Okay, let me make it again. This is where we are and this is where we want to be. This is where we want to be. So first, right now we're discussing the intuitive perspective of OLS. Okay, and then we'll discuss the mathematical perspective. So this is what I was talking about. This is the main discussion that we are doing right now. So this this formula gives you a scale of how much scaling. This formula gives you the magnitude of scale which is needed to scale standard deviation of x to b, right? To scale standard deviation of x to b. I mean, if b was 10 and standard deviation of x was 5, then this value 2 tells you that you have to scale standard deviation of x twice to reach this point B. And I have already told you what's so special about this point, right? It's the average point, and that's what makes it special. See, the best fit line minimizes RSS, right? it should pass through a it must pass through a region where um, the majority of the points are lying, right? It must pass through a region where the majority of the points are lying. And as I've already told you that there are only 2 points are needed to uniquely identify a line. One of the points is one of the points is actually fixed, the x bar y bar. Now the second point is this point only, this particular point that I am currently highlighting. These 2 points are actually the ones which make the best fit line, the average point of the data set and the x bar y bar point. Why? What is so special about the average? Again, I have discussed it in detail above, that the if again you don't have any outliers and unskewed data, then average is a very good measure of majority, right? And if your best fit line passes through a very high density region of points, right, which in which the average point will be lying, right? So the average point will be lying in the high density region of your data set. And if your line passes through those regions where most of the points are lying, then this is the thing that you actually wanted, right? You wanted to have the best fit line. This is what the best fit line does, right? It actually tries to while minimizing the RSS, it actually tries to cover the the it actually tries to cover the variance. It actually tries to cover the variations of maximum amount of points. The majority of the majority of the point it tries to cover. It tries to explain the variance of the majority of the points. Okay, so what the best fit line does is it actually tries to cover the variance of the majority of the points. And who better than the average point to take help from, right? Who better than the average itself to take help for this purpose? These 2 points are the ones, and this is the line. This is the line of our best fit. I'm so sorry about this. Fuck. Okay, assume it to be a straight line. Okay. Now, why we had chosen standard deviation of x here as our so you can say this is our kind of baseline. Baseline is the one from where the line by default. So this line is line by default because it is made by known values. So so standard deviation of x and standard deviation of x, it is it's actually a 45-degree line if you notice, right? Because if the x coordinate and the y coordinates are same, then the slope comes out to be 1, right? The tan theta comes out to be 1. So it's actually a 45-degree line. So it's actually a very good what should I say? Yes, it's actually a very good baseline kind of, because what better, because if you know a little bit of trigonometry, then then you must be knowing that this line, let's say this is 45-degree, tan theta, tan 45 is equals to 1. Any angle which is less than 45 gives you a value theta which is less than 45. The value of slope of that line comes out to be less than 0. I'm sorry, not less than 0, between 0 and 1. So it's greater than 0, but it's less than 1. And any angle which is greater than 45 degree, so tan of theta which is greater than 45 degree has its value greater than 1, right? So this is actually a very good baseline to start with. And this is what we are doing in our OLS as well. We start with a very standard line. I mean, what's so standard than tan 45 value whose slope is coming out to be 1, right? So this is the baseline that we start with, and then we make rotations either on this side or on this side to get to our best fit, right? As I have said before that I'm sorry. Yeah. As I've said before that the line of the best fit rotates about uh, rotates about this particular point, x bar y bar, right? The line of the best fit rotates about x bar y bar, right? Now the starting line is this particular line. The baseline is the starting line which actually rotates. Let me choose black. So this is the starting line. Okay, this is the starting line with tan 45 degree. This is the baseline for all of our regression problems. This is where we start with the tan 45 line, the most standard line possible. I mean, what can you assume more standard than tan 45, right? So this is where our assumption starts. This is the baseline, and from here this line rotates in anti-clockwise manner according to our assumed data set. If our data set would have been something else, it could have rotated clockwise in this manner, but according to our data set, it has to rotate counterclockwise, anti-clockwise to get to the best fit line, and it rotates about this point. It rotates about this point x bar y bar, and eventually after rotation it gets to this line. Okay, it gets to this line, right? It gets to this line. So this is our line of best fit. So what happened? We started with a baseline, and then after rotation about x bar y bar, we came to our best fit. And you can say how much this particular expression, or this b upon standard deviation of x, b upon standard deviation of x, it tells you how much to rotate. Okay, so b upon standard deviation of x tells you how much you have to rotate, how much rotation you have to perform to get to the line of best fit. This ratio gives you the magnitude of rotation needed to get to the best fit line. Okay, so this is the intuitive perspective. There's one more thing that I want to discuss, and that is called that I have named as the mathematical perspective. That is very easy actually. But first thing, this is the juice of the this is the juice of our discussion. The discussions that we were having till now, that the rotation point that I have made in the first video, plus the amount of prerequisite knowledge that I have that we have discussed in this video as well, to get to this point where I can say that this ratio, which we are actually calling as which we are actually calling as the slope, b upon standard deviation of x is equals to m. It actually tells you how much rotation you need to perform from the baseline. The baseline is the 45-degree line, the tan 45-degree line. So how much rotation you need to perform from the baseline, how much rotation you have to perform from the standard line, the tan 45 line, to get to the best fit line. And after performing that rotation, congratulations, you have reached the line of best fit. So this is what I think this ratio does, and this is what I think the ratio is doing. Okay, let me breathe a little bit before I'll discuss the maybe the mathematical perspective as well, which I was thinking that maybe it'll be better to discuss it in some future video, but it'll just take maybe 2 or 3 minutes more to discuss that as well. So I won't leave that for some future some future video, which I think I won't be making, maybe. So let me pause my screen recorder and have a bit of water before we move on to the mathematical perspective as well. Okay, I'm back. So right now we have just completed our intuitive perspective of the OLS, and now we will move on to the mathematical perspective of OLS. Now this is actually very easy. Let me make the dummy data set again and finish it off real quick. So this is your x bar, y bar, this is x bar, y bar, and let's say that this is our point of standard deviation of x, and this is our point B. Okay, now as I have already said, this is a square, therefore this value is also standard deviation of x. I hope I'm not making it messy. Wait for a while, I will draw the axes for you in a more clean manner and get back. Okay, as you can see that I've drawn the axes, and now it's looking very beautiful. Okay, so this is standard deviation of x, this is standard deviation of x, this was our square, and this is our very special point, x bar, y bar. This let me draw that point as well, the B point. Use another color maybe. This is our B point. I'm drawing them too perfectly, I guess. Too good to be true, right? Okay. Oh my god. Thank you so much. Whatever it is. So this is our B point. This is the length B. And as you have studied, what we actually do when we find the tan of an angle, the tan of the angle is what slope is, right? Um, Tan theta is slope. So the first thing that I have told you before, that this is the point there to that we need to get through, and the equation, this is the line, this is the point where we need to go. This is the our kind of desired point, kind of, you can say, to be the desired point. Then and the equation that we got after doing all of our manipulation was b upon standard deviation of x. Okay, so this is the equation that we got, and I'm claiming that m is equals to b upon standard deviation of x is giving you the slope. This is the point that we need to. This is our second required point, right? We need 2 points to uniquely identify a line. We had one, and now we have another. This particular point. Okay, so let's find the slope. It's actually very easy, right? This is that angle theta. The tan theta, or the m, will be equal to, if you have studied trigonometry, even a little bit in your if you have studied trigonometry even a little bit in your high school, then it shouldn't be very hard for you to find out. Tan theta is just opposite upon adjacent, which is, so tan theta, or m, is equals to this length, this opposite b, upon the adjacent, this length opposite b upon adjacent, which is standard deviation of x. Did you notice something? These two values come out to be the same. Did I miss something, or am I tricking your eyes or something like that? Actually, I'm not. This is the advantage of a square. Here, in the previous perspective where I have discussed which I have named the intuitive perspective, I should have named it the scaling perspective, because I actually focused on this part only. In the previous, in the first, in the discussion of the first perspective, we have only discussed, um, we were only focused into this portion, right? And therefore I made a scaling argument about this line, that this ratio is telling you how much you have to scale to get to this point. Now that we have kind of broadened, the horizon is kind of broadened, and what I'm saying is to look it as a whole and see that these two values are actually equal, because it's a square. Squares have all the sides, squares have all the sides equal, right? Squares, all the sides in a square are equal. Therefore, this value b upon standard, this value b upon standard deviation of x can be assumed to be this side or even this side. I mean, nobody is stopping you to do that. So if you focus on this side, then we have our first perspective. The first perspective is intuitive. It's not a very good word, right? Intuitive perspective. Maybe I'll give it another name. This should be this should be called scaling perspective, or scaled perspective, maybe. And if you focus, okay, and you focus on the whole, if you focus on this diagram as a whole, then you get to the mathematical perspective. Mathematical perspective, right? The mathematical perspective is easy. I've just used the basics of trigonometry to show you that because our denominator figure was a square, standard deviation of x and standard deviation of x, and standard deviation of x and deviation of x. It has four sides, and all those four sides are equal. It's a square. Therefore, you can use the scaling argument or the scaling perspective to kind of explain what's happening over here, what is actually happening over here, what is happening over here, right? Or you can use the triangular perspective, maybe the mathematical perspective, the kind of broadened point of view, to just take out slope directly, like what you have that you like what you have that like what you might have done in your high school. Tan theta is equals to slope of the line. So this is kind of a broadened perspective, right? We have kind of zoomed out of that, zoomed out of this particular line. We have zoomed out of this line, right? So, okay, this is what it is for this particular discussion, and see you in the next one. Thank you.